Okay, so we've learned a whole lot of probability by now. And I know that the vocabulary can get a little intense, but it'll get a little better. All right, but it's important to note that so far we've only talked about classical probability. Classical probability is characterized by counting things. The whole point of classical probability is to count things. We count the total number of ways in which something can happen. We count the number of ways in which a particular event we are interested in can happen, and then we divide those two to get our probability. It works great with a standard example like flipping a coin. Say I have this coin. We have eagles on one side. We have heads on the other side. If we wanted to flip this and find the probability that we get heads, well, classical probability would tell us that there's only one way to get a heads. There are two possible outcomes, so it would be 1 out of 2, which is a fraction that's equivalent to 0.5, which is the same thing as 50%. The odds of getting heads are 50%. That works great with a coin. It also works great with a die. We have a die here that has 6 sides to it. It's a fair die, which means that when I roll it, each side is equally likely of occurring. So what if I want to know what is the probability that if I roll this die and it lands on a 4? Well, if I roll it, okay, so it didn't land on a 4, it landed on a 3. So what is the probability that it lands on a 4? Well, there's only 1 out of 6 sides, so the numerator would be a 1, and the denominator would be a 6, so 1 out of 6 is the probability. Again, works great as long as each outcome has an equal chance of occurring. Okay, but what if we're looking at a situation where we don't have equally likely outcomes? Consider a Dixie cup. What if we're going to flip this, right? We're going to pop it up from the side of the table, and we want to know what are the odds of it landing this way. Okay, we're going to call that the top down. Well, we know that it can land on its side, or we can land with the bottom down, or the top. So there's only 3 possible outcomes. Classical probability would tell us that the odds that it lands this way, the probability that it lands top down, is 1 out of 3, 33%. But we all know that doesn't make sense. Why doesn't it make sense? Because they're not equally likely. It's not equally likely that it would land this way versus this way versus this way. Therefore, counting the number of outcomes and counting the number of favorable outcomes in this particular situation doesn't make sense. Classical probability does not apply. This is where empirical probability or experimental probability comes in. What it simply means is that the only way for us to find the true probability is to just do it. Do an experiment, do it, and figure out what is the likelihood, what is the probability that it lands this way. Obviously, lots of variables come into play, and that's something you have to take into account when you do your experiment. Okay, so we want to know what is the probability that if I flip this cup off the edge of a table, it'll land upside down. So the only way to find that out is to do an experiment. That's not good. That's 2 that went bad. 3, 4. Finally, on the 5th try, I got it. So that's 1 out of 5 attempts, or 20%. Okay, that might be the probability that when I flip this cup, it'll flip upside down. Well, how confident are we about that? Well, I only did it 5 times. Maybe I just got lucky. Maybe if I did it 100 times, I'd find that I hardly ever get it to do that. Or maybe I find that I was kind of unlucky, that I actually can get it a lot more frequently than 20% of the time. So what we have to do is repeat this experiment over and over and over and over again. And the more that we do, the more confident we are that our results will actually approach the real answer. Though we will never actually get to the real answer because we don't really know what the real answer is. Is my ability to flip this upside down truly 20%? Is it 21%? Is it 14%? right? We won't really know. But what we do know is that the more often I do this, the more confident we are that our results will be approximating the real answer. Now let's try it with 10 cups. So 3 out of 10. 3 out of 10. So now we're at 30%.
Okay, so approximating probabilities using the empirical approach. The probability of event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. The formula is frequency of E divided by the number of trials of the experiment. In my case with the Dixie cups, I got 1 out of 5 the first time I did it, which results in 20%, and then I got 3 out of 10 the second time I did it, which results in 30%. So which is the correct answer? Well, there isn't really a correct answer in empirical approach. The best we can do is just to repeat it over and over and over, and as the number of trials increases, as we repeat the experiment for a large number of times, the more we do it, the more confident we are that our results will approximate the real answer. That brings up the law of large numbers. As the number of repetitions of a probability experiment increase, the proportion which a certain outcome is observed gets closer and closer to the probability of the outcome.
Okay, now let's try something else. Log on to your MyMathLab account. Select our course, Math 150. On the left-hand side, you will find a menu. Select Multimedia Library. And then select Applets. And select Find Now. Okay, so we have a list of available applets provided by Pearson for you. And right here under Chapter 5, we want to use this one, Simulating the Probability of Head with a Fair Coin. Select that. Now, of course, a fair coin means that there's an equal chance of getting a tails as there is getting a heads. And from our previous work, we know that that has to be 50%. But let's pretend that we don't know that. Of course, classical probability is what told us that the odds are 1 out of 2 or 50%, but we're going to pretend we don't know that, and we're going to approach this with this simulation. So if we click here, one flip, so it simulates flipping a coin, and in this case we got a tails. It keeps a running track of what has occurred. We're keeping track of how many times we get a heads. So far we have 0 heads out of 1 flip. So if we stopped right now, we would say the probability of getting heads is 0 because we did it once and we didn't get a heads, so the probability is 0. Of course, we know that with empirical probability, we just have to keep doing this over and over and over until we are more comfortable with our answer. So let's do it again. It's 2. Okay, so now we did it twice. We got 1 head, 1 tails. We got exactly 50%. So someone would think, well, we stop now because we have the answer. Well, remember that we are pretending we don't really know the answer. We are going to be using simulation to find out the probability of things whose answers we don't really know. So we never really know when we have the answer. So it isn't really the point that we have 50% right now. We have to keep going. So we do it again. And this time I did not get a heads, so now I have 1 heads out of 3 total flips for a total of 33%. If we stop now, I would think that the probability of getting a heads is 33%. But again, only 3 flips of a coin is not enough. We got to keep going. So I'm just going to do it a few more times and keep track of what's going on. We're back to 50%. Do it again. We're above 50% now. We're at 60%. We are at 3 out of 5. Do it again. Do it again. Okay, we're at 71%. At 75%, if we stopped right now, I would think that flipping this coin, the probability of getting a heads is 75%, which we know is not true. So we just have to do this over and over and over and over. I'm at 80%. I'm at 81%. I'm at 83%. I'm at 84%. Wow. So we might start to think, well, is this coin even fair? Maybe it doesn't have a 50-50 chance. Well, again, just 13 flips of a coin is not enough for us to determine the probability of flipping a coin. We have to do this a lot. So I'm just going to switch over here to this button that lets me flip it 1,000 times, and we see what happens. Now we're all the way down to 51%. You see how for a little while we were way up here, right? But as we flipped it more and more, it got closer and closer and closer to 50%. Notice that we're not exactly at 50% even now after we've done it a total of 1,000 times. We have to keep going. So we can get closer and closer and closer and closer to 50%, though we're never really going to get exactly 50%. But the law of large numbers tells us that as we do this a large number of times, we get closer and closer to the theoretical probability, the result that we get from our classical probability approach of 50%. So with, let's see, 13,000 heads, and out of 26,000 attempts, we get about 50.31%. Okay, we've talked about classical probability, empirical or experimental probability. Finally, subjective probability. The subjective probability of an outcome is the probability obtained on the basis of personal judgment. For example, an economist who predicts that there is a 20% chance of a recession next year would be a subjective probability.